Thank you, everyone, for joining today's PRACE XSEDE webinar. As some of you might know, about a year ago at this time, well, actually more than a year ago, PRACE and XSEDE have been looking at ways to support researchers who use both infrastructures, and there would be some real things to be able to do if they could work together in a more reliable fashion with software interoperated a little bit better. And so 3 research teams were selected last year at about this time to really take some sort of pilot program at what interoperability might look like, but with some science goals as well. So now, about a year later, we're going to hear from the 3 teams about how it's been going and what they've learned along the way and what they've been able to accomplish. Our first team is led by Shantanu Jha from Rutgers University. He works also with Peter Coveney from University College London and Dieter Kranzmuller from LRZ. Shantanu, I'll probably be brief with the instructions here since we have so many speakers, but please start your presentation, and thank you to everyone else who is on the webinar for joining today.
Thank you, everybody. Begin, just want to check that as I move the slides, people are able to see the movement as well. Great, thank you again. So Nancy, Ralph, thank you for the opportunity to, first of all, be part of this XSEDE PRACE project, and also the opportunity to present on behalf of Peter and his apologies for being doubly committed at this time, not being able to join. The perspective I want to take for this presentation is of cyber infrastructure and federating cyber infrastructure, the definitions of cyber infrastructure. Favorite definitions actually comes from which emphasizes the importance of the people, not just the actual physical resources, and obviously the networks and the connectivity between the people and the networks and the infrastructure. This project is really about the infrastructure, the infrastructure, facilitating 2 complementary sets of skills across the Atlantic, and infrastructure serves as a nice foundation, but also a nice opportunity. Respective scientific skills, if I may say so, to get in a common science problem. Peter needs any introduction. Peter's a world-class chemist who's spent the better part of the past decades making advances in methodological approaches and for free energy calculations, amongst many other things. I've been working in the area of performance distributed computing for the past 10 years or so now. And I just do a couple of things. I just try to understand interoperability at a conceptual level. And over the past years, my team and I have spent a lot of time trying to support the many simulations mode of computing. With philosophy that I think there is a need for these ultra mega single simulations that scale to 100,000 cores, 1 million cores. But which is more associated with those? If you look at where the real science, or I should say the bulk of science, is going and needed, what is needed in terms of computational capabilities, the need for supporting many simulations approach. These could be heterogeneous, these could be coupled, these could be uncoupled, there could be different forms of coupling, which by some accounts some people would like to call workflows, but I'll not open that can of worms because I think is a workflow. Is that the Peter's expertise and my team's expertise is the fact that there is a very large set of important scientific problems in general, but in particular in that Peter has specialized in, namely finding free energies of biomolecular systems. And my research, which has looked at theoretical aspects and implementation aspects of how to support many systems running on distributed as well as high-performance computing. What you see today is a manifestation, or I should say a snapshot of that research that that has been in progress for at least 7 to 8 years. Peter and my collaboration goes back for the operation, and hopefully the beginning of many, many more. And a critical component of which has been facilitated by this project. So I'm not about this very specific, too much details about this very specific problem which we've been using this project to investigate. But just to set the context, it's about HIV drug resistance and the fact that there's variation in the proposal in the HIV structure, and that makes the set of drugs that are currently used and the proposed drugs susceptible to become effective very soon. Think genomic revolution is to address this problem, microbial resistance, other kinds of resistance and mutations, but one approach to cocktail of drugs to a patient's specific genomic profile. It raises many questions as it answers. Well, isn't that the purpose of good research? But one of the problems that it does open up is how do you manage many, many millions of simulations, possibly of lengths, possibly of varying capabilities. So that's the full problem. Obviously, we're not solving a million simulations here. So Peter and his team over the past years have been looking for essentially an end-to-end workflow. Now, at some stage, I could wax lyrical. I could give lectures on the difference between general-purpose workflows and domain-specific workflows and why the latter is the right way to go as opposed to the former. But this is not the time or the venue for that. What Peter has essentially done is he's created a domain-specific end-to-end workflow, which he calls the binding affinity calculator. It's actually we call it problem-specific. No surprises. It's to reliably predict Just give me a second. Sorry, the window is. My slides are being obscured. I apologize. Right. Back is to be able to predict the binding affinity of these compounds without posing any of the significant details and challenges that are inherent in the end-to-end process. I should lay out that I talk about millions, but any specific problem could have order 10,000, 20,000 different simulations, depending upon the problem being studied. Right? And the big objective here is to be able to rank the binding affinities of various drug candidates. Okay. So now the computational challenge, having hopefully understood the high-level scientific goals, to the binding affinities of these drug candidates using one very long simulation. If so, you principles or hypothesis, time averaging over space averaging should ultimately, in the thermodynamic limit, work out to be the same. What's seeing is almost schism in the entire biomolecular sciences community as to what is the right approach. For an amount of computing time, employ a single long trajectory approach, or should you decompose the long trajectory into many smaller trajectories, so essentially replicate the system with the starting points and for shorter durations. This is a question that has had similar incarnations or has had many different incarnations in many different fields, and I'd be glad to hear about other fields as well. This community in this biomolecular simulation space, this has acquired a particular interest. On the one you have the people like D. who have special purpose machines in order to really push forward the state of the art in the single long simulations. And a large number of us have been trying to respectfully disagree with that approach and saying, if you think about this carefully, well, you're going to get more bang for your buck in the other direction, namely by many larger simulations in quantity. And it's very complex. It goes down to the inaccuracies in the parametrization of the force field, so on and so forth. But the Peters, and we've published a paper a couple of years ago, which acquired a bit of attention at the AS and elsewhere in NSF that up. He shows for the first time that if you employ you get slightly rated, but you fair to say uncontrolled errors, and more importantly, the result errors are slightly unreproducible, and we can get into the fundamental reasons for that. In the paper, we looked at the when you run not a single long simulation, but you reproduce your ensemble-based approaches. And we find is for a set of 9 drugs, the FDA-approved drugs for HIV, the errors are in control, smaller, but those are more reproducible. So it's interesting. I mean, if you think about it, it's really getting down to we are doing whatever we can do computationally, but deep algorithmic and formalism reasons for doing what we're doing. So the algorithms, formalisms, and the cyber infrastructure, the software, working in tandem. The protocol employed, any good scientific experiment should have a well-defined protocol, is out here. There were 50 replica ensembles for the various science problems. To determining what's the number of replicas. Again, the constant here in all of these experiments is the fixed amount of compute time. If you change that, then obviously the parameters that I laid out on this slide, 50 could soon become 100, depending upon how much computing time, or could just as well become 12. So the other 3 parameters, the duration of the projector around 4 nanoseconds, as opposed to some mammoth efforts of approaching a microsecond. So again, there are details in these papers written mentioned below and in others. The nutshell here is that the single simulation is not as reproducible, and as I say, Peter likes to be emphatic. He likes to call it unscientific. I try to take a slightly more ecumenical approach and say it's less forceful as it may have been once upon a time. So, and here's more details, death by graphs here, but the real important things are the fact that the profiles as produced by the ensemble-based approach are also more natural from a statistical physics distribution. Okay, and again, for those of you who are in this domain, you may want to see the paper referenced here with all the gory details. It's a 25-plus page. This became the starting point of our work. Some of this work was done as part of this project, but also some of the cores were already developed, and we've been trying to grow since. So just moving forward, and this was a BBC article and a few others that picked up the fact that supercomputers can help in a better design of drugs in the future. So I've laid the context, I've set all of this out. So what's the computational aspect? So I've been working for 7 or 8 years together. Some of you, at least Nancy and I, talked about this back in 2005 when I won the Supercomputing HPC Analytics Award. And some of you, I don't expect you to remember, but might remember that the problem for which Peter and I won the Analytics Award at Supercomputing was for computing this free energy profile of in this case, a polymer locating across a nanopore, a protopore or a nanopore, irrelevant at the level of detail. Very large simulation, 400,000 fully solvated, 400,000 atoms in a fully solvated system. And we spent, as a matter of fact, my 1 whole year of my postdoctoral research was spent in coming up with an algorithm that does to not run the single long simulation, but be able to recompute the free profile of translocation along the axis of the equilibrium simulations, and showing that you can actually recompute the equilibrium free energy profile. That's the details if you're not from this field, but basically it was established algorithmic formulation that non-equilibrium simulations, in this case, many smaller simulations, had the fundamental capacity of reproducing the equilibrium property you get from a single long simulation. The algorithms and the fact that we at that time got TeraGrid to make some initial progress was, I think, what impressed the supercomputing judging committee. As I like to now say, it was a big lie. Not lied, we would never intellectually resist. But we've set up the problem, we've developed the algorithms, and you know what? The AeroGrid can now help solve this problem quite easily. We just have to run about 1,000 to 10,000 MPI simulations of 512 cores each. That shouldn't be too difficult, and that's what we presented. The next 2 or 3 years, I moved on to the US. Bought this big lie. He thought we had solved the problem. He hired me at CCT, and we had a student back at UCL running these simulations. And you see 2005 to 2009 to run a plus MPI simulations of 112 cores each, so that he could reproduce the equilibrium free energy profile. I mentioned in the slide, it did not go off very well. It was a quick time to solution, ended up being a highly protracted time to solution. We got the answer, and that's why you see the cover of a very important in chemistry. So we met with a lot of grief. To catch the scale, on the one, we tried to do 1,000 to a few thousand MPI simulations because order for us to get that done. What I'm trying to tell you is the kind of science that Peter's doing as part of this binding affinity calculation for FDA drug. For that very paper, we probably did at least as many simulations in 2013, 2014, and we're now doing more. Well, what is the availability of some fundamental actions, computational abstractions that support the simulation view? Right? Again, the details here, I'm sure time is short. I just want to point out that what was a single job effort, one by one, we created a set of abstractions which supported the collective execution of many jobs. And remember, these are not entirely uncoupled. They could be, but they're not entirely uncoupled. There's a simulation phase, there's an analysis phase, there's a simulation phase for the particular problem. Radical cyber tools, the set of tools and capabilities that I've been working on for some years. And 3 aspects that you need to know about radical cyber tools is their explicit layer to the heterogeneity of infrastructure. We all know is a fundamental attribute to use distributed cyber infrastructure of the type, whether it's null to XSEDE, i.e. micro heterogeneity, at a macro level between XSEDE and PRACE. You write abstractions to manage the heterogeneity, and again, I've spent the better part of the last decade thinking of the right approaches to manage this heterogeneity. But it's a necessary condition, it's not a sufficient condition. A sufficient condition, I believe, is, along with the heterogeneity, the ability to have flexible execution and post-management techniques. And my slide will be about a specific approach to this, which we call the pilot abstraction concept. And many ways to look at this. It's a lecture or several lectures unto themselves, but the primary aspect here is that you have a container job, which then is a container for the largest, smaller simulations, and control over the execution, the resource assignment to the smaller simulations, which is highly non-trivial. Part is that these components, the heterogeneity, the resource management there, they are solutions unto themselves. They be extensible and usable by higher tools, higher level libraries, so forth. So one of the fundamental design consideration of landscape changes, you're now thinking of prolif building blocks or building blocks. And the coupling with Peter's back in. The binding affinity calculator, radical cyber tools, is what is known as HT-back, high throughput binding affinity calculator. In this combined capability, we've run the back, which earlier was not able to run on a broader set of resource infrastructures. And I'll illustrate just a few here. Arch book, thanks to Dieter and Helmut, and obviously all the XSEDE resources. I like to call this as saying it is the matter of 2 appropriate capabilities, interoperability for free, and more flexible resource utilization modes. So here's the landscape of the 3 important components. At the top, you have at very bottom in yellow, you have the Saga layer, and in the middle, you have what is the resource management layer, but specific incarnation of which is the pilot abstraction. I will leave you with Saga and the Python implementation coming from my group, but remind everybody that it's a standard. And I have a joke in my group, which I call Radical's first law, is to start developing adapters for different heterogeneous infrastructure. Think of phenomenal waste of time and human resources, and NSF should, I'd say, ban any project that claims to write another adapter for another infrastructure. By the way, this has been done, and it's been done in a standard form. Yet people continue to do that, so I will not begin that battle. Just want to say that at least 4 or 5 different years, a dozen groups solve this problem, and the problem has a name. The solution to that problem has a name called Saga. Let me just speak very quickly to the pilot layer. Again, there are 20 different pilot jobs out there. Everyone spun up on their own for a very specific reason, for a very specific infrastructure, for a very specific usage mode. For the 4 years, we've been sitting down, analyzing these 20 different pilot jobs, trying to define a common minimum model for pilot jobs, because pilots mean different things to different people. The result is a theoretical model of what constitutes a pilot job and what does not constitute a pilot job. That's called the P-star model, and there's more to it. And the implementation of the P-star, a reference implementation of the P-star model, just like there's a reference implementation of Saga, is called the Radical Pilot. Some of you may know the earlier incarnation, Big Job. The viewer thinks the number of not inappropriate jokes associated with the name, so we thought we'd give it a slightly more revolutionary name, hence Radical Pilot. And heterogeneity, and it's important to appreciate heterogeneity, especially in the interoperable context of this project, is assessed at many different levels and different dimensions. One particular approach that requires addressing is the Saga, the access layer heterogeneity, but at some level you also have to counter the local architectural heterogeneity. Just a long-winded way, I will not get into the details of the slide, of that some of the heterogeneity also has to be handled by the layer, and our architecture of the pilot layer is designed, considers the fundamental changes that you encounter or differences you encounter going from machine to machine, and that is local changes are localized in what is known as the pilot agent, a structured approach, scientific approach to managing the heterogeneity, yet not losing some of the performance and flexibility that is needed. Another lecture, so why the focus on pilot jobs? Well, there's a lot of reasons for using managing resources flexibly. If there's something that distinguishes high-performance computing from multi-site high-performance computing, the fact that the traditional high-performance applications, your monolithic MPI jobs, they have a static mode of utilizing resources. You ask for 100,000 cores, you use that for the entire time of the project. You typically divide, slice, and dice that between different tasks. Solutions of MPI will obviously exist, but today that is not state of play. And in high-performance distributed computing, what we're talking about in this many simulation mode approach is the ability to have a final level of control. Now, people say, why don't you just stop trying to do these pilot job things? Just ask for the right amount of cores in the first. We have papers out there which are predicting the ability of a particular size is fundamentally a few tasks. The process is chaotic. I do not use chaotic in a light way. I use chaotic in a technical extreme sensitivity to initial conditions. And so the attempt at actually using this to profile your jobs to run quickly is definitely assumed at the start. And that can't beat the process and not actually start predicting the right resource profile. The right thing is to be dynamic adaptive. Hence the focus on pilot jobs. The right action for the right scientific problem. And then pilot provides a simple but elegant unification of HPC, HTC, DC, and high performance. And so makes redundant this nonsensical debate that goes on in the community. Is it HPC or is it HTC? Is it distributed or is it parallel computing? Set of arguments. Here's an abstraction that renders all those arguments irrelevant. And third, but very importantly, it's a building block. It's used in many different layers, high, above, and back is just one example. Examples. So this is where trenches going on, making hopefully scientific core conceptual and formalism advances in the domain of biomolecular simulations, bringing in, and happen as a consequence of deep research in computer science and cyber infrastructure. And this has been ongoing, is ongoing, and will continue to be something that occupies our time and energy. And this is all possible thanks to our respective teams, but also thanks to Nancy and the XSEDE team for making allocations available on XSEDE, in particular also to Dieter and Helmut for helping short-circuit some of the bureaucratic processes at PRACE and providing us with a very quick allocation of $1 million on book. And I am completely in omitting Mark Parsons, who also provided a special allocation on Archer with Dieter on SuperMOOC, and obviously use our regular set of allocation to use a very, very large heterogeneous set of resources ranging from Archer, Hector, SuperMOOC, regular XSEDE resources to non-XSEDE and non-PRACE resources. You will know of the world-class Center that's upcoming that's up and coming in Britain with access to Blue Gene. So our work is a combined not only XSEDE and PRACE resources, but also Blue Gene machines at the Hartree Center. With that, I'd say thank you very much for your time and attention. I'd be glad to answer any questions.
Thank you very much. Do you have any quick questions for Shantanu? I see that the attendance list has been growing steadily during your talk, so that's probably due to the sun rising here in the U.S. I have a question if no one else wants to jump in just yet. So you've been doing large-scale distributed computing for some time, Shantanu. I wonder if there was anything different about your experience this time, anything that was better or worse, or kind of how have things changed since that 2005 experience on the TeraGrid?
Great question, and I think it gets to the heart of, whereas I say things are hard, but there is definitely a measure of progress at every level. The has only increased over the years, and therefore, if not tackled properly, has potential for becoming a more difficult problem and possibly proper. But thanks to sustained effort over the years, we've learned how to manage the heterogeneity, and not just manage it in the sense to know how to respond to it, but how to heterogeneity. There's a word about managing complexity is not the same as exposing simplicity. And what I think we've managed to do is do a bit of both. We've enabled Peter and his team to the simple way, with a simple model, conceptual model, as they want to. So one, we've realized the management of the heterogeneity and complexity into one or two well-defined layers, and we have experts handling the heterogeneity. So again, we've been saying, Nancy, that the core remain, but are of heterogeneity, which, as we discussed, is a fundamental feature of high-performance distributed cyber infrastructure. But we better how to manage it and not have it permeate across all layers. So in that way, the experience, at least for Peter's group, has been way better thanks to the right abstractions. So for a group, we know how to manage that and keep it localized. I hope that answers your question.
Thank you. That's good to hear. Any questions for Shantanu from folks on the line?
Yes, Shantanu, Jules speaking. I'm actually interested in your between XSEDE and PRACE sites. Did you really use communication between XSEDE and PRACE sites, and what has been your experience with that?
When you mean communicating with people on either side?
No, from your pilot jobs. Did you run jobs the data sources?
Yes. So let's be careful. This is not one pilot job running across XSEDE and PRACE resources. No, a pilot is confined to one machine. And it runs that machine. And then
But what I understood is that you met it from another, or
yes, so it's distributed computing. We sit on a laptop, which could be at Rutgers, could be at London, wherever, and London to XSEDE machines as well as to PRACE machines without actually physically having to log into those machines.
you don't need specific network communication between sites. You don't have large requirements in that respect.
Correct.
Yeah.
Thank you, Jules.
Question, Jules. I know XSEDE is starting to look at some software-defined networking options in the coming years. I don't think we have scalable networking today, but that would be something interesting to think about across the site. Any questions for Shantanu? I know too that Tabitha Sale has joined. Tabitha is our lead XSEDE support for this project and is also going to be speaking the contribution of the speakers today for XSEDE 15 this summer. Do you want to go ahead and load your slides? You can put the desktop. Oh, there we go.
This one on? Someone from the audience hear me?
And the slides look very good also. Morris Riedel, is that how you pronounce your last name?
Thank you.
Probably. From Munich will be our next speaker. Morris is going to be speaking to us about his PRACE XSEDE collection, which involves large-scale earth science data. I see that some of it's also being presented at the Research Data Alliance meeting here in San Diego next week. Are you going to be here for that, Morris, or is there someone else presenting that?
The authors of this work, Marcus Götz, will be there next week. I can't, unfortunately.
Okay, I'll be there and I'll look for that also.
Marcus, let's see.
Why don't you go ahead?
I would invite you to come to the RDA Big Data Analytics session. It will be interesting. I think it has quite some overlaps with processing needs in PRACE or XSEDE.
I'll look out for that one. Thank you. With that, I'll let you get started on your talk since we have also Sandra Stefan, and I want to make sure everyone has time.
Yeah, thank you very much for the opportunity. In contrast to my previous speaker, Shantanu, we are much more on the data side. So what we actually were exploring were the term data analytics, and with this, what kind of technologies are there or are required to perform data analysis, or recently also known as data analysis, or across XSEDE and PRACE. More, let me just say a few thanks also to some of them that I didn't put here on the slides. So you see some PhD students, but also I would like to thank some work that was included of bringing parts of it on the Blue Gene queue, which is Michael Stefan from the Unicore team. So there are definitely more. That's why I put et al. Here. Andrew Grimshaw was here as a visiting scientist and installing and helping us with GFFS on the Blue Gene queue. More to this, and I have an acknowledgement slide. It's just not possible to put all of them here in front. Anyway, another those that are here on the front will not also present. So Shabbos is with me and will take over the second part, which is then more technical, specific solution. So let's the outline that we thought would be very interesting for the audience. First of all, everything we do should be motivated by a scientific case that we outline and that we had in the project proposal. If you it was mostly focused around the earth sciences domain. We also do neuroscience studies. This is the one we tried for several small projects, I would like to say, in technology assessment, in terms of really figuring out what is the pay basically to go away from the numerical simulations that we know to more data-intensive works. Looking at R, looking at different technologies and how they could, say, more obviously support big data frameworks and what's actually out there. So I think it is that we have lots of results in terms of technology assessment, and that's what we promised. You see a quote here from our proposal. So then we didn't ask for resource allocation or something, so we actually don't needed any runs or so. For us, much more a point of are the configurations that are required for data-intensive science. What type of technologies exist, and also with the paradigms, right? So if some of you recall, you cannot easily bring a MapReduce job on MPI. Although frameworks often promise that MapReduce jobs, for instance, have a lot of data-intensive science problems. So a lot of technologies we investigated, we picked one particular problem. We basically note as a scientific case and provide a solution. Compare with the existing solutions here that are ready to use now. So everything we have here in place can be used over standards and the interoperability that exists in XSEDE and right now. Here and there, things need to be configured, and that's what we will explain in the talk. Again, the point, the technology is there, but of course, if you would like to be using it, you have to have resource allocation. So everybody here in the webinar or later on looking at this should be aware of, you can theoretically do this, but of course you have to get grant allocations in PRACE or XSEDE to get calculations done. We'd like to start with scientific cases, and we put 5 in this project. I will quickly go through while focusing on one. So in this case, this is basically data coming from different aircraft, where we largely looked into how well supported is R across the infrastructures. And we found, while discussing with many sites, that R is typically quite supported, and this is what you, for instance, use in this particular case study. Then to the events part, which was, let's say, more eventing across different chain locations like storms and so on. We found that there's a specific requirement to use something like we call array databases, not traditionally supported in XSEDE and PRACE. So we figured out and basically tried to solve that and evaluated this, how this could be, let's say, put in an HPC environment like XSEDE and PRACE, and found out that this is actually not that simple. So it requires root rights, it requires sounds. So it's technology which requires much more investigation if PRACE or XSEDE would like to use these kind of technologies. Another one we just recently invited was Rasterman, where we also looked into. It's another array database, but it's very suitable for location data sets. And activities in the one that we have with the Asian systems, also from the geosciences, we looked at small frameworks feasible. For instance, the GIS system has a scientific gateway, which is very promising, provided by Xiaowen Wang. And as far as I know, this is already on the track towards XSEDE. So some to go ahead with this, and with this you could use different infrastructures. So all of these different projects basically have some results in one way or another in terms of technology assessment. Here on the webinar, we would like to focus on one, and this is this Pangaea lighthouse that we call it. And the problem that you see on the left-hand side, basically, there's a huge open collection of data sets. The line of open sciences will be expanding significantly in the next years. You see quite the graph increasing right exponentially in the last couple of years, and it will basically follow. And this is where we starting with data. It's not only about the volume, right? It's also about the different variety that we have. You see that on the bottom with different profiles, seabed photos, air photos, outer records. In particular, in this webinar, again, we would like to focus to have a concrete solution here for a problem, and time series analysis that we would like to show some possible, let's say, frameworks and algorithms that solve this problem. So this is this particular one that we picked out of these 5 to show here. In the paper, we would write possibly more, but given the time constraints, I really focus here on this one. And the data problem is given by the situation that there is an autonomous measurement device everywhere. It's in the air, in the ocean. There's a cabled observatory in the Korea Fjord. So there's lots of data collected. And in the past, more and more have looked at this and did manual quality control and the search for interesting events, of course, and studies. But this is becoming more and more difficult. There's a scientific case here that this needs to be automated, right? Do outlier detection with simple studies, but if you have big data growing and growing in the next years, this is not only a problem for the Korea Fjords in Sweden, but notably for the whole Pangaea open data collection. That's why we created this case, looking at some, let's say, more automated ways or semi-automated ways how to actually detect outliers in this data, and in particular here we have time series measurements basically in the Korea Fjords. And now what basically can XSEDE or PRACE in terms of technology provide in order to solve this problem. So, of course, basically published other work or so already in light here, where we have results at the EGU, which is the European Geosciences Union 2014 conference, where we had initial studies. It brings us to the discussion and to the point why we need a DB-scan algorithm. So this is a typical class algorithm, as we would call that in data mining. One of it, which is really strong compared, for instance, to k-means clustering. It's called based spatial clustering of applications with noise, hence deviations, DB-scan. And it was actually, it's a quite old algorithm, if you want, from 1996, introduced by Martin Ester, and it groups numbers of similar points, as you can see on the right-hand side, and different distant measures you can use, like for instance Euclidean ruler distance, as we would call this. And you see on the right-hand side what it does to your data. It takes, let's say, unlabeled, uncluttered data and gives them a meaning, groups the data, makes a density measure, for instance Euclidean. The interesting side effect that this algorithm or this particular algorithm has is that it's not only able to work with various clusters, it identifies outliers and noise. For instance, in this time series that we have in Pangaea, for example, as noise. A very critical part why we choose this algorithm in order to fix that problem. So this is a technical requirement, case study. But it's now basically more in the literature how it works. Of course, there's a bottleneck that lots of these data must be in memory. So it's the first constraint. And also about the time series we're facing, we even go for 10 years or 20 years time studies, where of course this all will not fit in memory. Hence, the part for a parallel and scalable application of the algorithm comes into mind. And another that we would like to particularly focus here in that contribution is that it's very critical to find the right parameters with it. There are 2 parameters called epsilon and min points, which you can see on the smaller graphs, hard to see. Let me just explain it here a little bit more broader, where epsilon is the kind of or disk where you basically have a number of minimum points at least to foster. So you can see it as 2 constraints, but finding these 2 parameters is easy, right? To do parameter sweep studies in order to find the right ones. And in particular, this is a drawback of the DB-scan algorithm partly, that with changing series or with changing days, you always have to adjust the parameters on the fly. So if you have a time problem like the time series, you really have to have lots of these parameters in fitting your data in order order to see whether your parameters are actually right to solve the problem. So now that we have two different, we have on the one hand side quite some parameters we have to adjust and submit often. And on the other side, we also have parallel and scalable needs because the data set will not fit in one particular system of small size. Hence our technology assessment. And this was quite, let's say, surprising because many of the frameworks we looked at were the ones typically referred to as the MapReduce ones or high throughput computing ones. We're starting off Apache Mahout, a very famous machine learning framework on Hadoop base, which does not offer any DBScan implementation. And surprisingly, also the Apache Spark machine learning library, just recently being more and more momentum in the data and machine learning community, is really not supporting parallelization of that. We have Python because Python more or less has quite some momentum also in scientific communities, but also there is no parallelization strategy for DBScan. Of course, here usual serial tools like R or RETL, MATLAB, and so on. Because some of the data sets in the time series, you most probably get a big problem anyway. Only ones that were applicable to the PRACE and XSEDE environments in our technology survey published this and basically, or we submitted this to a data bank for more information. Please feel free to contact us. Two here highlighted, which is one that we created ourselves. With ourselves, I mean one of my talented, or two of my talented PhD students. Basically compared them with the existing MPI implementation Northwestern University provided. Let's address a little bit the parallelization results. So this is really, how we scale to the order of magnitudes we would get from the time series. So we had a very smart big data pre-processing in terms of different cells. So you combine the kind of density-based clustering here with grid-based clustering. There are also like hierarchical and so on clustering methods that are there, but here we have a kind of hybrid of two different approaches, which makes this scale. The implementation is free available, OP and MPI can be used together as a hybrid application. Different pre-processing steps that you can see on the spatial grids. We don't even necessarily require adaptive mesh refinements like used in the numerical situations cases. And we have some optimizations in place where I cannot go into for time reasons. But you see the references, there's a very nice web page where you see all the details about this particular tool, which we found most notably useful. And it's one of the key results here from our technology assessment. And with this tool, given the allocations in the future, we are very, I think, looking forward to time series issues. When you compare this with the comparison of the existing runs we had from the Northwestern University, very quickly that we have a nice speed up here on the right-hand side, but you use necessarily big cores, which is another finding, right? Data mining, we're not filling a full bloom gene queue. We talk here in this speed plot, for instance, of 512 cores. But also consider that this is just one data mining run, one parameter setup. Think about what I said before, finding the right parameters in that sense. This is really a tough issue, and then requiring lots of different parallel runs or runs. I think Chantino called them replicas, something like this, basically lots of them in parallel. But more notably, you see on the right-hand side also the low memory usage that we basically have here when you compare to the other. So far with some applications as a proof of concept. Again, we don't have the big allocations yet, but this will probably something as part of the PhD study with the Pangaea dataset in the future. And quite much works out, so we are very confident that it will also scale to the large Pangaea Earth science data collection. You see point cloud, which is another clustering problem. We used it with all the data is available on the U.B2Share. You can, let's say, use the data. The same is true for Twitter. We uploaded Twitter data where you can basically reproduce the results, which is another interesting aspect here of these findings. I point out that this algorithm implementation is free. The implementation is free, open source, and if you want to work with us on this, please give us a hint. Let's go to the second problem, right? We're scalable and parallel. That's what we kind of solve with this tool. What is more important in all the parameter studies, where we will later see how XSEDE and PRACE will solve this in an interoperable way. So we see here these two parameters. When you want to use it in a typical, let's say, job script, you have some dependencies like HDF, which is a parallel I/O framework, and you pick two parameters which are related to this, and these have to change. And here a real run, basically, that is performed here on just on a supercomputing environment with, let's say, different types of data volumes, which in the data mining field already quite interesting from the terms of volume. Again, if you think about that, you had to multiply this with all the number of parameters. And the output results are typically written in the input. What you know is, of course, you mark each point while you sweep through the data set with this kind of notion of the density. Also will basically give not only the number of cluster, you will each point assign a label to which cluster it belongs. So the output and the input are the same data. So you have to always copy this. And if it's much more runs, you quickly come to the point that it is very tricky to work with all the data inputs and outputs. But more importantly, for a given application domain problem, while the cluster is basically sweeping through these different points here, it will also have those as noise which are not fulfilling the minimum points requirement. And we have outliers. Now you easily foresee that a time series would be equally possible when you plot a graph with a series, and there would be outliers which are extraordinarily far away from the normal distribution that you have. So to sum up a little bit what I talked about. So the main challenges we really had when using this, and again, lots of these things are uploaded where you can reproduce it to yourself on your system. You will find out that changing the different parameters, but using the job scripts again and again and change them for different or CPUs that use resources, right? We tried Mason now, we tried Judge, we tried different resources everywhere with different scales. So you have to have different job scripts as well, which is quite annoying. Then you have various dependencies on multiple versions from the implementations like GCC, HDF, which you need in a particular C++ installation. Hence, you see the configuration issues faced as a data miner when you want to just use it. You see module loads here in front, where typical data mining, my faculty in Iceland, for instance, working with me would be never knowing and basically don't want to waste time with. Then we find the right parameters, min points and epsilon, but you quickly see there are some other parameters you also have to think about, like most notably the data in and the data out. Working with these data locations is quite, let's say, tricky. So all these are challenges we pose now at the point of saying, well, XSEDE and PRACE has technology to engage in this. And with this, I would like to hand over one of the research scientists in my research group, which is actually working on this particular field, who is Shabazz, and will tell us a little bit about how we addressed the challenges of this.
Thank you, Maurice. Hi, everybody. We took this as a challenge from application scientists, and we leave application scientists to edit the job scripts and also applications on different platforms, and also in sending jobs, submitting jobs on different resources with different parameters. So we were discussing at one point that why not we just use a middleware solution and use a standardized protocol so that multiple sources, architectures or infrastructures can be accessed in a very seamless and what we say unified manner. Considering XSEDE architecture, so on the right side you see an XSEDE architecture with a lot of elements. So we specifically focused and took the management part, and we analyzed that the standards are really viable solutions to the automate the process of solving this DB scan algorithm across different sites, like job runs on different sites. And we took the common protocols that are actually deployed on XSEDE and PRACE at the same time. So in XSEDE and PRACE, the most common standards and implementations we have available is from OXA Basic Execution Service, which is OGF standard, provides services a SOAP-based, web-based interface for managing and monitoring jobs. Interfaces are concerned, these are the major interfaces that are used to manage and monitor the singular and multiple jobs at once. As the job request model is concerned, we use the job submission and description language, which is a very common and well-adopted standard to specify the job requirements while submitting or entering the batch system via middleware. So, and not only JSTL as a pure specification, we took a lot of profiles. It has a lot of helpful profiles and extensions like HPC profile, HPC High Performance Computing Basic Profile. Most importantly, parameter sweep, which is a very useful extension in this case for solving data miners' problem of running multiple jobs in one request. So you can specify a formula in that sweep across multiple parameters in one go. And it's implementation dependent. How do you want to implement it? That you want to run multiple jobs on, or you want to model this request in one job which has multiple inside this one contained and composite job. Third, we used SPMD, which is a single program multiple data, that is actually more specific towards specifying or accessing requests with respect to parallel parameters. For example, MPI environments, or the variables that are required for MPI environments, like for example number of processes, thresh processes, etc. So we by using these standards, we of many edits of jobs, scripts, because middleware has all the configuration. It actually encourages the according to the platform or according to the implementation, the realization of the architecture. And finding the right parameters like min points and epsilons in terms of this application. So I would rather also emphasize that this will not only help this application, it can also help other applications. We have other applications on the roadmap that will also benefit from this standards-based suite of available specifications. Now to the problem of working with locations of distributed data inputs and outputs. So we used a technology from XSEDE. It's called the Global Federated File System, Genesis team. So, and this was the solution that we used to automate the process of data hosting and data storage and data transfers as well. So we are in some kind of a, I would not say maybe, it's still say data cloud, but it's kind of a data file system which is globalized across XSEDE PRACE. So we have one installation and PRACE as well. I think at UQueen we have one endpoint of GFFS, so that we can place the data anywhere in GFFS and can be accessed by any XSEDE resource without any issues. This proper security setup is available. We see the actualization of the request. So how we express the request in JCL using this extension. So it's only what we say a unit job. It's not a parent job. So you can see all the application with a lot of parameters, and all the environment settings are actually hidden. So this is the middleware job and middleware responsibility to edit this job and run it on any platform which has this configuration of application, or which has proper figured MPI platform with this implementation. So yes.
This is Nancy. I was just wondering, I think to Florian also, does the webinar, does it have a hard stop at a half hour past? 30?
Hurry up, yes. So
I just want to make sure Sandra has time in case the webinar quits in
No, this is no problem. The webinar will continue this, but of course we have to keep with the schedule.
Yeah, okay, thank you.
Will not be kicked out then.
Sorry, that we are hosts. So these are the, if you see in the slide, these are the parameters that we want to sweep across in different in applications in different domains. See at the bottom how the application will look like if there are multiple runs. So you have TV scan -e with different values, multiple min points and multiple epsilons, or what we say set density or set radius points in the density base cluster. So, and the proper realization of that how we represent this requirement in a file using parameter sweep extension of JSDL. So we wanted to sweep the epsilon and the fourth argument of this application across from 3 to 320, for example, with step 10, and similar to the case with the min points. So you see that how simplified it is for the user. For example, I would user maybe for a client user interface that actually creates JSDL, generates this JSDL, can easily simplify the problem of a data mining expert. He can specify, represent an abstract job with it in nature. So next slide. And this is the middleware implementation, or what we say deployment perspective, how we perform initial runs, because we just started these runs on both sites, so Blacklight in Pittsburgh and Judge. I think is on the way on the deployment, so it's under progress. We used client desktop Genesis to middleware, and for GFFS implementation, we used deployment from XSEDE, which is like ubiquitous across XSEDE and some of the, I would say, one PRACE site. These for the job runs, we are using the standards-based program to express the job requirements and the job requests. So you see how one client can access and can make multiple runs to analyze the application and data sets across different architectures and different infrastructures as well. So just to share a snapshot of how the results like through the GUI interface provided by Genesis 2. So you see how just a creation of the application output that I think Maurice also showed you, that you have set of clusters and resultant output through the common GUI interface by user, like XSEDE user, for example. So to mention one more thing, that for accessing the resources, we used my proxy service provided by XSEDE. So, users from XSEDE who have the XSEDE account can easily run jobs across both infrastructures. My proxy and the architect experts in XSEDE. To conclude, on behalf of Maurice and me, so what we presented so far is a scalable and parallel DB-scan algorithm with different implementations. We took some implementations from MapReduce and from Northwestern University that we found that are not scalable, or either they have very unfriendly license. That's a new implementation in-house. This is parallelized implementation with very less code, I would say, and very less set of requirements in terms of applicability. So this is our implementation, a contribution from Yulish. And XSEDE and PRACE interoperability, we thought it's helpful to use the common standard-based common standards that are available in both XSEDE and PRACE projects. We raise parametric nature and all the tools that are available on these resources. So thanks to also PRACE team who helped us deploy application and also enabling us through Unicore to those endpoints. So next step, we like to we've launched this approach, and we want to automate the application accessibility of support vector machines implementation. We have another application in the what we say in the back. It's actually also dealing with some use case with the earth sciences and the remote sensing area. We are also considering to resource allocation calls for XSEDE and PRACE. And And also in the upcoming RD and EGU sessions, we'll have this our application and implementation. I'd like to present it there as well. So finally, I'll thank Robert and Andre from Bremen, and Rick J. Scott from Pittsburgh Computing Center, and also XSEDE operations like, for example, Vita and Victor, for allowing us to use these resources without any hitches, and also providing Unicore endpoints. And the Unicore team, the Unicore core development team, and PRACE and XSEDE staff. So you're welcome.
Shabazz, thank you very much for a fascinating talk. Do we have any quick questions while Sandra is staging her slides? I had a couple of things. Sorry, go ahead.
I have a question, Morris and Shabazz, about the GFFS. What is your experience with the performance? I mean, did you really share it in Pittsburgh and Jülich, or only locally? That was not so clear for me.
Yes. So it was actually so accessed by both the endpoints, the Blacklight and also Judge. So only requirement was for us to install the extended package of Unicore and Genesis and install the Genesis client. So it was the requirement by both the endpoints Blacklight and also Judge, and through the extension, both the endpoints can access this GFFS file system as the user known to the GS server and also the structure.
And what about the performance? Did you?
Yeah, performance. I actually am not the member of the GFFS. I wanted to use the technologies, and I'm also not a promoter and a developer of this technology. So I leave it to the Genesis 2 team, so you can communicate with Genesis on further performance related issues.
Yeah.
You didn't.
Was not necessarily our major goal, but still we had the Bremen data, and this worked okay.
My question basically, did you experience any problems using GFFS? I mean, how do
of course, big data in that sense, right? So
okay.
We had normal data sharing.
So the data density, the magnitude of data we used was 2 GB per job. So it was okay. The performance was fine. So in like transferring data back and forth in jobs.
Let's say for us it's fine, but of course we would recommend some more evaluation studies in detail on this particular issue, maybe, right?
Yeah. That we can also use grid FTP as an alternative solution in file transfers. So both can be used seamlessly in Unicore.
Also note, while Andrew was here and we had this installation with Michael Stephan, who is in charge of the Blue here, also discussion with Thomas Eickermann, and we looked deeply more into the security, because that was more where I've been concerned with the fuse driver and things which normally are also not standard here. And all this was also marked as green as far as I had from the discussion, so everything was okay and in line, so that we can really, as the European supercomputing, operate that, right? While in other issues with scientific gateways and group accounts, the best technology seems to be in line with security regulations here. That's more our focus than performance, to be honest.
really important? Of course.
Thank you very much. Let's switch over to Sandra's slides now, please. There were a couple of things that I'll have to follow up with you later on, Morris and Shabazz. I was really interested in the availability of code that you wrote, HPDB scan. It's open source and already tuned for these architectures for analytics from multiple domains. I think that's something we're really interested in XSEDE, and be interested in how we can get that kind of installed and advertised. Alan, I think it would be
helpful in doing this, so would be quite interested to take this up in XSEDE and PRACE.
Terrific.
Have a follow-up.
Sounds good. I see that Alan Sill is on the call, so I'm sure he was happy to hear about how the the existence of standards contribute to the ease of use for this project, and Jim Basney was on and has since dropped off, the MyProxy developers. So several folks on interested in components of the work. I had some GFFS questions as well. I'll follow up later on all of those things. But talk, really interesting to hear that the code can be applied to earth sciences data, sensor data, Twitter feeds, also, and be so kind of flexible for different domains. Andra, I assume you're promoted to a presenter, yes. Is from the University of Notre Dame. Her project involved also the use of Unicore and the Science Gateway MOSGrid, which is a chemistry gateway that's been in operation for some years now. Sandra's unmuted. We can't see slides yet.
It's right between. So now, nice. Okay. So, screen, that should...
Up now, very good. Thank you.
Yes, we see the slide.
Screen, I hope. Okay. So thanks for the opportunity for the project and for this talk. So much focuses on science gateways for informatic applications, specific workflows in digital systems, and system really usable for users, especially in groups like biologists, chemists, which are not really often IT specialists, but have to. I mean, if you would send me to a wet lab, I would have a problem to do the experiment. So that's a good collaboration always. Now for 1.5 years in the US, and in contrast to my speech before, I don't have really a team at the moment. Hopefully mid of this year that works out, the grant I got, and but fantastic fruit for cooperation. So I would like to thank directly the MOSGrid team who contributed to this work, and the developer and his team of the PyCon GPU code. That's the code for plasma physics. And Abbas and the Airflow are European projects and using WSP grade as underlying technology. They helped also with setting up. And of course, I would like to thank XSEDE and PRACE teams and people I have direct contact often with to accomplish this project. So 2 use cases for the PRACE XSEDE project. One is targeting the molecular simulation community, MOSGrid Science Gateway. The project started in 2009 and now continued by EU projects and via the XSEDE startup. And the PyCon GPU is targeting the computational radiation physics community. It's one of the particle in-cell algorithm in plasma physics. And the idea is to simulate first what is measured, so to experiments. And it's very interesting that we have the international communities already existing, the collaborations to apply for this project. So that's on the one side MOSGrid, it's a German instance with some European affiliations and international collaborations. But in MOSGrid we have the problem that we have German resources behind it yet. We would love to have more resources behind. It's, with authentication and which certificates are allowed. So we have to deal with that. And with Cybers, we had the chance to use our resources internally also the airflow with the different communities in there and ComGem. And on the US side, we are working is a group at the University of Cincinnati. The radiophysics code that was developed at the Helmholtz Centrum in Dresden. They have really very national collaborations in Europe with extreme infrastructure, the XSEDE project, and all of in Europe and in the US. So the MOSFET use case, there are three domains, that is quantum chemistry, molecular dynamics, and having different codes there, like Gaussian and WChem, GROMACS, XSEDE. And WChem and GROMACS, for example, are both available in XSEDE, Unicore resources. GROMACS is also available on PRACE resources. Gaussian, I've seen that it's also available on some resources in XSEDE at least, but I have still to find out what are the licenses which you can really use it, because we had a problem in Germany, and that we couldn't offer it to every user, international user who was affiliated with a German institute, and are compute and data intensive. The three research domains are quite different from each other. They are all on molecular relations. For example, you can split the data very nicely via different infrastructures. It's very parallel. Then you can start the jobs and start it on XSEDE resources or PRACE resources and get that back. GROM, for example, has also an NPI version and a GPU version we can use. Of the MOSFET Science Gateway was always to share workflows, also to have meta workflows that users don't have to pull the workflow together from scratch. If they have these mini workflows, they know that it's designed for a specific use case. We have distributed data, and of course the users to share all the knowledge. So experience and in the MOSFET community, they share workflows. 90% of them would share workflows. 80% would share even their data after they have published it or they have a patent. So that's because we want to have this platform to really that the user communities can benefit from it and don't repeat experiments or can start with data they get from other co-authors on experiments. In the MOSFET instance and tree, we work with Unix XtremeFS and continue working with Unicore because we use some nice features of Unicore directly in the Science Gateway. XtremeFS is distributed data management, and also using it still in the German instance, but we'd like to go in XSEDE to IRAS. So all these points, professional collaborations, international resources with a single point of entry. We are using X509 user certificates and SAML as the credential data transfers because we offer in the portal that a certificate can, proxy certificate can be changed to a SAML version or created from it. The advantages SAML has with the maximum hops for delegation. And so it means that you can set up, like hops are only allowed, and if someone tries to use the SAML as a baby and has, that he's really a user, he's not able to use it more than for a count of number of hops. visible for different single sign-on infrastructure. That was the decision why we did this already for the German instance, but we are using it now also for the XSEDE PRACE instance. And for the users to use Unicore is the portal directly to which resources they can connect without that they have to sort out which resources are available. And they can get a list of all tools available at that point of time, and they can put together their workflows without they have to upload something. Of course, tools have to be installed on the resources. It has to be integrated in the incarnation database of Unicore. We have the 3 domains, as I mentioned, and we are working with workflows, but also with portlets directly created for the end users, so that they can set up a job with certain parameters which are pre-configured. They can change it, but it's pre-configured for the resources, so that it's of the optimal use. And visualization for each domain. For molecular dynamics, we had a little bit about molecular dynamics before already from the speakers before. And it's always to minimize the energy to get to the most natural of molecular structure. And focusing on evaluation of the gender interactions, special design. For the you see here still it's JMO, so we are working. We have done quite a portlet CamDoodle to show nicer to show structures nicely, and MockCut is another possibility. With WebGL, both technologies and HTML5, and users can create visualizations and have features on to download them also for publication. So the XSEDE PRACE project was to the access to PRACE Unicore resources. The same features we have already in the German instance. So one point, of course, then the security with the certificate and SAML assertions we had to extend, and distributed data management is still relying on XStreamFS, so that's ongoing work that we want to apply IROS. And we have shown the list of tools that users are really able to put everything together without being that the job is started on where the software is not installed, or that their workflows cannot be created or submitted because software background available. So the challenge is that we change authentication to seed account for the Moscow Science Gateway. Has the meta workflows. Thinking of meta workflows, with the meta workflows means that already for certain resource, for certain tools, and other users who have totally different credentials want to use them also. So we have to find users who can start them and read with them. We want, of course, to use the incarnation database to have information about the available tool or resource, and integration of IROS with Unicore. That was because of the distributed data management. So what accomplished is at the moment that the Science Gateway a certificate I can easily create on XSEDE site. proxy certificates is JPS. And this I can upload into the Grid US. For instance, not Grid US, but we also integrate PRACE there, so we will rename it again. And so we now from this proxy certificate directly a summarized version that can be used for the jobs. And if you have a look at the docking workflow, it's a really complex workflow with preparing diligence, preparing the actors. The users don't want to each of the boxes to check the properties, so we are just creating their workflows usable. And workflows we import for the quantum chemistry community in the instance. What you first workflow is a meta workflow, and other ones, except for the hello, the NWChem workflows are small workflows which are integrated in the first one, so that it looks like this, and it's much easier and more for the user to work with them. So work at the moment is that as we can discuss that maybe after talk or later, coming back to that. So I have to apply some XSEDE rules for science gateways, because we talked about that there should be one science gateway certificate. How to submit really from a science gateway jobs, and that's so suitable for most grid features, especially if it's distributed data management. So the users have their own user space, and if they don't get their own user space for their data anymore, as I mentioned, they would share data, 70% of the users, but they don't have the that they can protect their data, they wouldn't like to go for the science gateway. Another what's going on at the moment is to have an automatic authentication in line with the XSEDE account, so that the user doesn't have to fill in his address anymore. Use the incarnation database to have all the tools available in the list. That the user has this available. We are porting more workflows for GROX and NWChem. On the integration started. Plasma physics side, this PyCon GPU is the first scalable GPU cluster implementation. So this class in the background, PI, and then the CUDA toolkit. They got the prize with Gordon Bell finalists in 2013. For international collaborations, yeah, the international GPU process would be ideal. They have a really fantastic scalability, up to 10,000 GPUs. They have proven that once. Of course, they don't have always 10 GPUs available, and not each of their use cases needs so many. But also up to 1,000 or 500 would be fantastic for the collaborators in this field. I like this picture very much because it shows one of their experiments. And plasma, after shooting with laser on aluminium foil, and they set up this experiment. I did first the simulations, how to set up the best way. I really have the best starting parameters they can have a look at. So to have access to XSEDE and Unicode GPU resources, workflows for easing the use of the software. So it's easy to to install it open source. But start with parameters. What is the best to pre-process data before doing it? And obviously, we are working on the authentication via the XSEDE account. We would take the work we have done from it. We are working with the researchers themselves on creation of the workflows, what use cases that they can create simple workflows as starting point for collaborators. And we want to use UCOF for the GPU resources. So I had some challenges here. Maybe I'm too honest with this slide, but the time on my side, so I'm the PI of the project, was a little bit constrained. And so that's a general problem in academia with projects which have no financial means. I still emphasize that writing with XSEDE and PRACE was great. Will further on great. I only had some time problems in between being in this situation, having not yet a team, writing proposals. I don't want to whine. It's only therefore we had some time constraints in the project. Policies on access to XSEDE and PRACE. So we should really discuss this topic with the Science Gateway certificate. That's so in Moscow and also for the high GPU other matter. And because GPU resources, it seems that Unicore in XSEDE at least has not many GPU resources behind. So resources are there, fantastic, but via Unicore. So from the project was if PRACE would be in favor of that, maybe we could write together a grant for use cases to get NSF funding. Means are available to do more use for both communities. That would be fantastic. That's attention. Any?
Thank you very much. Any questions from folks on the line for Sandra?
Hi, I have a question. Shabazz here. Firstly, thanks Sandra for a very nice talk on Unicore. My question is about what technology or what kind of workflow framework you're using for this Science Gateway. Unicore's core workflow engine, or you have your own workflow engine?
That's great. WC Grade and GU are the from Starkey in Budapest. We are using workflow technology, and the nice thing is that you can really distribute each job of a workflow to different resources. It's very nice if you have the distributed data management with Unicore, for example, integrated the data, the jobs is then not brought to the different locations, but just via the distributed data management tool.
Okay. And my second question is, so what is the stopper for having Unicore with GPUs? I think it's not an issue. So we have PRACE sites which has GPUs with Unicore accepting and exposing these HPC site resources and capabilities.
Technical issue. There's no technical issue. It was only that some, or let's say the GPU resources we are not available via Unicore, but widely used also for other projects. Don't get me wrong there. It was for this project I couldn't use them because it was not Unicore.
Okay. Got it. Thank you.
Yeah, I was going to ask, I know Stampede's got some GPUs. Which machines in XSEDE were you using, Sandra? But in general, there's a shortage of GPUs in XSEDE. Yes, that's.
Oh, it's not a shortage. So Stampede is great. I use it for another project. I only cannot use the GPUs from Nicor.
We'll have to check on that. Yeah.
Yes, Nancy, I think there's some special configurations you have to do on the back end to these to be available via Unicore. With the task force to see if that's been done.
Okay, this is exactly the sorts of things these interoperability projects were to cover. So very. Thanks for a very nice talk. I think, I'm partial to Gateways, but I think they provide a nice interface as far as kind of simplifying the underlying complexity of using multiple sites. One of my questions was going to be Unicore very much newer on XSEDE resources than is on the PRACE resources, I would say, and did you run into any issues? But I think that's kind of all come up, so those were actually some of the things that we wanted to learn.
Oh, but it would have been if I would have, asked whether we could do that. But, yeah, I'm still continuing this work to.
Yes, Tabitha.
Sorry, I was just going to say, Sandra, if you have any trouble with any of the Unicore sites, just loop me and try to exceed and try to smooth things out.
I only mentioned it at the moment because I haven't tested now the GPU code yet on these.
Yeah.
But it was not a real technology process.
Okay.
So yeah.
No problem. Thanks.
Yeah, this will make things function for other users as Unicore gets more wide use and XSEDE. So thank you very much. I think with this we've run a bit over time. I know we originally were thinking about 30-minute presentations per team. Thought, oh, gee, that sounds a little bit long. Let's go with 20, but it's turned out to be more like 30 anyway. So thank you for everyone for sticking with this. I think it's been a really interesting session. I want to especially encourage our speakers, the folks Lon, Morris, and Sandra, to work with Tabitha on the XSEDE 15. Thanks for the very good idea to write such a thing, Morris, and we'll make loop Shantanu in since he's had to leave the call. But we'll be actively. Ralph Roski's also sends his apologies. He had some connection troubles this morning, had a meeting conflict, so he would have liked to be here also. I'm sure the PRACE and XSEDE teams will be discussing kind of next steps. I know that we would both like to do more area. I want Florian and Jules, if you have anything you'd like to add, if anyone else has any questions for our speakers.
Yes, Nancy, I would like also to thank all the speakers and participants of this webinar of today. It was nice to see the results of the PRACE joint call, and I had the impression that the selected project really paved the way for future collaborations. And I'm convinced that the project enabled a better use of the PRACE and XSEDE resources.
Nancy, it's Tal, and I'd also like to take the opportunity to thank the speakers who pointed out the subtle but underlying role of OGF-based standards in their work. It's not the sexiest thing to talk about, so we always appreciate seeing it. Please keep in mind that there is OGF 44 in May 21 and 22 as part of the EI Spring Conference in London, to bring a lot of groups together to continue this discussion about interoperability, and look forward to any other opportunities that are helpful to interoperability.
Thank you very much, everyone. I think that concludes our webinar. Florian, thank you for getting the WebEx. I thought it worked very well.
I was also very satisfied. Thank you all. Nice weekend.
Yeah. Yes, you too.
You too.